meaningfully apply product rule, quotient rule, chain rule, that you know the derivatives of the inverse functions. And if you don't know them, you know how to derive them, all those things. So a lot of you are already pretty much where you need to be on that. Others of you need to work more. Hopefully you can get there. But anyway, I will begin with a word of prayer. Dear Father, we thank you for this day and for the weekend is about to start. Help us to glorify you in what we do and just to learn a little more about your creation today, Lord. In your name I pray, Lord Jesus. Amen. So hopefully I won't start coughing maniacally in the middle of this lecture. It's anybody's guess what happens. So the last part of the course here is on what is largely known as integral calculus. And so there are two basic problems that calculus seeks to answer. The one question that calculus seeks to answer is the question of what's the best linear approximation to a function, which is essentially equivalent to the question of what's the best fit line to a function at a point. And so the derivative answers that question, right? The tangent line is the best linear approximation to a function. And we've used that idea to analyze things like minimums and maximums and rates of change and all kinds of things. But then the other question that calculus is loosely about is how do you calculate the area under a curve? And the thing we're talking about today is not that. Right, the thing we're talking about today is the opposite of differentiation, which is called antidifferentiation. It is truly bizarre that these two things have anything to do with one another. Why should the opposite of a derivative have anything to do with the problem of finding the area under a curve? And yet they do. Like, just to let you know, the fundamental theorem of calculus, this is the big idea for the rest of the course is this. If we look at the area under a curve, say from A to B, right? And this is y equals f of x. If this is, we're trying to find this area here. And if you have big F of x with df dx equals to little f, so this makes f an antiderivative. An antiderivative of little f. All right? Then the fundamental theorem of calculus, part 2, simply states the following. It states that the integral from a to b of f of x dx, and this is just a notation. It's a notation for the area from A to B under the curve that I've tried to shade on the whiteboard, which of course is impossible. But anyway, I miss chalkboards. Anyway, so integral of f of x dx is simply equal to f of b minus f of a. That is a profound theorem, that the area under a curve has anything to do with the opposite of a derivative. Why should that be? Yet it's true. And I'll spend the better part of the week after Easter, Monday, proving this. All right? It'll take us a couple days to explain why this is true. But that's where we're going, and that's why antiderivative is very interesting in the big scheme of this course, all right? That's the major thing we want to master for this semester, past this point. Well, using that is one thing, but the other thing we also want to get really good at is finding antiderivatives, all right? So the one thing the antiderivative does, the big thing it does, is it finds areas under curves in this sense, right? But it does other things, like antidifferentiation allows us to solve a variety of interesting word problems Like, let's see here, for example, suppose that the acceleration is the change in the velocity per time, right? dv dt is acceleration. Suppose the acceleration is equal to, let's say, minus g. All right, here g is equal to 9.8 meters per second squared, right? If the velocity at time 0 is equal to v sub naught, then find v as a function of t. So this right here is what's called an initial value problem. And that's what I'll be focusing on today in terms of application. See, because we can talk about initial value problems without knowing anything about that funny looking integral sign above, okay? So you guys tell me. I mean, fill in the blank. ddt of what is equal to minus g? What you guys help me out. Fill in the blank. What should I put there? What, if I differentiate with respect to time, do I get back minus g? G is a constant here. You're like, you haven't taught me this yet. How should I know the answer? Well, the answer is, you should guess. You already know how to differentiate, right? So ask yourself the opposite question. What would I have to differentiate to get minus g? Negative 9.8x. Your heart is in the right place. I take your x and make it a t, though. So minus, well, let's say, my bad, minus gt. Right idea. But make it a t and x, because we're differentiating with respect to t, right? See what I just wrote? If you differentiate that with respect to t, we get minus g, right? But think about something else. We could add any constant we want. What happens when you differentiate a constant? You get 0, right? Yeah. So I can say plus a constant, and that's going to be true. So this tells me, just by guessing, that the velocity at time t should be equal to like minus gt plus some constant, right? And if I didn't have any other data about the problem, that would be as far as I could go. But what else do I know? Well, I also know that the velocity at time 0 is given to be v sub naught. This is the usual notation we use in physics. We just call v sub naught the velocity at time 0. Just a typical label. So let's plug that in. So we got like v of 0 is equal to minus g times 0 plus c. So apparently this, and this is supposed to be equal to v sub naught, where we want to choose c to make this true. So this time we choose c equal to what? Not 0. C is equal to, c 0, that goes to 0. We got 0 plus c equals to v naught, so c is equal to v naught. So therefore, the velocity at time t is equal to v naught minus gt. There you go. That's the formula for the velocity as a function of time in the constant acceleration problem, right? Like that tells you the velocity of this marker as it drops, right? Like if I drop, initial has velocity 0, v sub 0 is 0 for me if I'm just dropping it like this, right? And then it accelerates downward. It goes faster and faster until it hits the table, of course. And I can do the other way around, right? I can throw it up like that. As it leaves my hand, it's got a positive velocity up. What happens? The velocity decreases at the rate of minus g until it becomes 0 at the top of the flight, and then it comes back down. Anti-differentiation, right, paired with fitting the initial condition gave us the formula for the velocity as a function of time. So that's a pretty obvious, like, nice application of anti-differentiation. We can do this again. Because what is velocity? Velocity is dy dt in this context, right? But we also know, we just worked it out, it's v naught minus gt. Now here the v naught and the g are constants, right? So here let's say find y as function of time given y at time 0 is equal to y naught. Now, of course, I could give you specific numerical values for v naught and y naught, but I think it's healthy for us to do a symbolic problem. So we're doing that. Also, if we leave v naught and y naught symbolic, then we've solved not just one problem, but all possible problems of this type. So, you know, rather than lifting one load of bricks up a hill, why not just lift all possible loads? It's the same effort, pretty much. All right, and we all need practice with symbolic problems, so here we go. Now you might complain, you're introducing a new concept and doing weird letter stuff at the same time. I know, it's true, I did it. Sorry, I'll get to less lettery problems. I teach the like teenage Sunday school at my church. I hear the students, they complain about, like one of my students, she's a little bit younger, so she has the math with just numbers in it. And then her sister has the math with letters in it. And it's like, it's horrible. The letters. So I guess you guys are, well, you're past that. All right, so so you guys help me out. So we want ddt, right, of something to be equal to v naught minus gt, right? What should I fill in the blank? What can I differentiate and get back to v naught minus gt? What should I put there? Minus gt squared. Excellent guess. So let's try that out. So we make a guess and we check it, right? So if we differentiate v naught times t, v naught's a constant, so differentiating v naught times t does give me v naught like I want. Very good. Differentiate minus gt squared. The g pulls out. What's the derivative of t squared? Well, it's 2t, right? So this differentiates to minus 2gt. That's almost what we want. Can we fix it? What do? Just divide by 2. So you divide by 2, that fixes it. Right? And then again, we can add a constant, right? Because the constant will differentiate to 0. So basically, anti-differentiation suggests that y is equal to, some constant plus v naught t minus 1/2 gt squared, right? And so if we didn't know any initial condition, that would be the best I could do. But we do know that the initial position is y naught, right? So now plug that in and see what that forces the constant to be. So we plug in y at time 0, and so into this formula I get c plus v naught times 0 minus 1/2 g times 0 squared, and that's all equal to the given y sub naught. So again, the constant ends up just being equal to the initial data which was given. It doesn't always work out that way, but this time it did. So c is equal to y naught, and lo and behold, we have y of t is y sub naught plus v naught times t minus 1/2 gt squared. So this is like an important baseline formula to know for physics 231 here. I don't know, about 10-20% of the first test is about this. Something like that. Of course, it's calculus-based physics, so I also want the students to be able to derive it like we're doing here. You don't just learn a formula and plug stuff in. I expect students to be able to do the calculus themselves. It is calculus-based physics. But anyway, I digress. Any questions? So, let me show you another one, which is a little bit sneakier. this will be our last example probably for a bit. But population growth, like dp dt, is equal to k times p. This is exponential growth. This is the differential equation, actually, which describes exponential growth. In other words, the yeah. Well, false alarm. So the rate of growth is proportional to the population. You know, the more people or the more bacteria, the faster the growth, right? So I guess I kind of gave it away with the label exponential growth, but what's the solution here? Like what? So the question is, if I want ddt of something to be equal to k times that something, what would I put in here? This is not an anti-differentiation, right? This is something a little bit weirder. So technically I'm outside the bounds of this lecture in some sense. Now if you read my notes, I show how you can make a substitution which changes variables into something that you can just anti-differentiate. But how about this? If we put e to the t, we'd get what? This is the derivative of e to the t is e to the t, right? So that would work if k was equal to 1. What happens if we put e to the kt? Well, you see that works, right? But the pattern of this one's a little bit different, right? You notice that if this works, then I can multiply the equation by 3 and it still works. I can multiply the equation by 10, it still works. Whatever, right? So basically I can multiply by a constant here and here. And that is still an identity, which is true. So this suggests that a solution to this differential equation actually has the form c e to the kt. Now what would be p of 0 equal to what? C e to the 0, right? So if we call the initial population p sub 0, then we get that the population at time t is equal to p0 e to the kt. Now I haven't really, my method for solving this was very ad hoc, right? It was just pure guessing. Yeah? So in differential equation, actually in calculus too, in the middle of the course you learn a calculational technique to derive this solution, all right? So I'll leave it for there. I just want to point out to you that this idea of if we have a differential equation, what is a differential equation? A differential equation is simply an equation that involves derivatives. It's kind of stupid, isn't it? So like this is a differential equation because it's an equation involving a derivative. That's it. Those were also differential equations. See? dy dt equals to this is a differential equation. dv dt equals to minus g is a differential equation. These are all differential equations, but when the differential equation has the form a derivative equals to a function of the independent variable, then we can use anti-differentiation to solve it directly. So like it's the special case. All right, enough about all this. Let us get into the formulas. So let's start working on the let's look at this. The other calculus section's ahead of us. No, look at that. I see evidence. They're like a whole week ahead of us. How'd that happen? Did we take a break? I don't think we did. Man. We'll end up in the same spot though, guys. All right, so help me out here. So what we're going to do is we're going to play fill in the blank. d dx of what equals to x? d dx of what equals to x squared? d dx of what is cosine x? ddx of what is sine x? Oh, thanks, Emma. So, so I should state a definition for us, okay? Definition, if big F has df dx equals to little f, then big F is an antiderivative of little f. This symbol here, integral of f of x dx, is equal to the set of all antiderivatives of little f. And the theory here is kind of neat. So if you had two different antiderivatives, how do they have to be related? Like suppose you had two different antiderivatives for a given function. How would those characters be related here? Like let's think about that for a second here. And then we'll get back to my fill in the blank game. So think about this. If you had df1 dx equals to little f of x, right? And that was equal to df2 dx. What would that tell you about f1 and f2? Maybe. How about this? They're equal is a possibility, but what if they're not? So in other words, this would tell us that ddx of f2 minus f1, right? That would be equal to f minus f, which would be 0, right? Do you see that? So like if df1 dx is f, if df2 dx is f, then the derivative of the difference of the antiderivatives must be equal to the difference of the function little f, which is 0. So if you have the derivative of the difference of two functions is equal to 0, what's this tell us? I think I was supposed to prove that this, I think I forgot to prove this semester, but I usually make a big stink of proving that if the difference of two functions has a derivative which is equal to 0 on a connected domain, that forces the difference of the functions, that forces that to be constant. So like, this means that f1 of x minus f2 of x is equal to a constant. Now this is, suppose it's on, the connected domain is important, see, because you could have different constants. If you had like disconnected, you could have the difference equal to one constant on the one piece and a different constant on the other piece if it was disconnected. So the connected is technical, important. But anyway, long story short, we find that if you have two different antiderivatives for a given function, they're just related by a vertical shift. See this? So at the top I have the set of all antiderivatives, right? The set of all antiderivatives. But you could replace this with what? So like the integral of f of x dx, we could simply write as big F of x plus a constant, where big F prime of x is equal to little f of x, and c is a real number. What do you think about that, guys? Like, so we have to write the set f of x plus a constant such that f prime of x equals little f of x plus a constant every time we do this? Well, no, here's the custom. So the custom is that instead of writing this, we just write big F of x plus a constant. All right, so this is shorthand for that set. Yeah. Yeah.
What does the leftmost equation refer to?
The leftmost so I'm using what's called set builder notation. So like the way this works is you curly bracket, stuff in the set, condition on stuff. So that's what that means. Like, so the things in the set are functions of this form, and the condition that what makes them of the particular form we're interested in is that the derivative of big F is little f, and c is just a real number. So it's called roster notation or function notation. Now, this right here is called the indefinite integral. Indefinite integral. So the indefinite integral is just a fancy name for the set of all possible antiderivatives for the function. And the little f has a name too, I should probably tell you. The little f is called the integrand. So the integral of the integrand is a token antiderivative plus a constant. All right. Okay, now that I have put you through this litany of notation, all right, you're happy to know that we don't write this set, right? In fact, most calculus books wouldn't even tell you this. They just make some kind of cagey, sketchy comment about it's the set of all derivatives, or they might not even say that. Well, anyway, let me shut up. What I want to say I shouldn't say here. So, and it's not even politically incorrect. So, anyway. So you guys fill in the blanks for me. What's the derivative of so what I want to put in the blank here is a token antiderivative. All right. So you guys give me. Derivative of 1 is 0 though. You gotta go backwards. The other way. Turn that frown upside down. Yes. X plus a constant.
X times a constant.
Nope, because x times a constant differentiates to a constant. Right? 1/2 x squared. I will take your c and put it in later. So let's just say 1/2 x squared. That's the simplest. But you're right. You could add a constant to that, right? You could have told me 1/2 x squared plus 10, whatever. But 1/2 x squared works. Is the point. So that is an antiderivative of x, 1/2 x squared. What can I differentiate get x? Yeah. 2/3 x cubed. Guessing is good, but we have to check our guess. What happens when we differentiate 2/3 x cubed? We get 2/3 times 3x squared, right? But 2/3 times 3 is 2. That would give us 2x squared. Right idea. Just take that 2, make it a 1. We're good. So the derivative of this, when I differentiate x cubed, I get 3x squared. 3 and 1/3 give me 1. That's an identity. So that's the antiderivative of x squared, 1/3 x cubed. What can I differentiate and get cosine? Sine. All right. Well, that was easy, wasn't it? What can I differentiate and get sine? Minus cosine. Hey, you're doing better than my friend. All right. So let me now that these are 4 antiderivatives. All right. What are the corresponding indefinite integrals? This is, you're like, well, why do we need this? Well, we need something to recognize the ambiguity in the addition of the constant. That's important for applications because it refers to the possibility that we have different initial conditions for solving an initial value problem. Like the constant is the flexibility to fit different initial conditions. So anyway, here we go. The integral of x dx is 1/2 x squared plus a constant. The integral of x squared dx is 1/3 x cubed plus a constant. The integral of sine x dx is cosine of x plus a constant. The integral of cosine x dx is minus sine of x plus a constant. There you go. There's the indefinite integrals, which I will just generically refer to as integral. All right, so context should make clear whether we're talking about a definite integral or an indefinite integral. We haven't even defined definite integral in here yet. I wrote it on the board as a motivational comment at the start of class. So like that thing I've got in the box way over here, this thing, this is a definite integral. So what's the difference between a definite integral and an indefinite integral? A definite integral, provided it exists, is a number. All right, so a definite integral is just a number that describes the signed area under a curve. In contrast, an indefinite integral is actually a whole family of functions, any one of which the derivative would give me back the integrand. That's the difference between these concepts. And as I said, except for the thing that I'm erasing, it would be totally mysterious why on earth we even call these things the same word. Like, why are they both integrals? Because one has to do with undoing undo a derivative, whereas the other is an interesting geometric statement about the area under a curve. Why should those have anything to do with each other? Well, that's a mystery. That's a mystery that was hidden to the ancients, but was revealed to Newton. So this is why Newton and Leibniz get the credit for doing calculus, despite the fact that there were ancient Greeks and ancient Chinese who were very much doing the same calculations as calculus. They just weren't doing it with the full understanding that Newton and Leibniz brought to bear. Let's do more of these. I'm going to use the indefinite integral notation because it's just helpful, all right? Okay, so example, so you guys help me out. Integral of x to the n dx. What do we, so we've done a few examples. If I've got x to the n, what should I do? So you guys are going to make a guess, and then we're going to check your guess. Yeah.
I think, would it be x to the n plus 1 divided by n plus 1?
X to the n plus 1 divided by n plus 1. Yep, plus c. And his generic point of calc, like test 4, if you don't add the c, I have to take a point away, you know, because I have to teach you guys to add the c. It gives me no joy to take off a point for not adding the c. But I have to do it. Anyway, so, but you guys are going to add c, so it's fine. The other thing I'll take a point off for is if you don't write the dx. That's not just decoration, that's important that it goes there. It plays a vital role in calculations going forward. But you're exactly right. And let's check your answer. Let's check your answer. So d dx of x to the n plus 1 over n plus 1, right? The constant differentiates to 0. We don't care about that, right? So this is what? 1 over n plus 1 times what? Times n plus 1, x to the n plus 1 minus 1 by the power rule, right? So the n plus 1s, they be canceling. And that's x to the n, which is our integrand. That is what must be true for the integral to be legitimate. It's a legitimate integral if when I differentiate the integral, I get back to the integrand. That's the way it has to work. So like a picture of what's going on is this. The integral of f of x dx is equal to big F of x plus a constant. It must be that this takes us back to here under differentiation. And that has to happen. All right? Now, do you care to tell me when your answer doesn't work? But you can think.
It's because I did this before, so I still remember
You still remember this?
bits and pieces.
Well, forget about remembering things. Let's just think. Let's just think. We don't need to just remember things. We take ownership of things, understand them for ourselves, right? You know. When does this formula break down? That's right. N equals minus 1 is a big problem because that would give us division by 0. All right, so let's ask the question. Integral of x to the minus 1 dx, what's that? Well, that's the integral of 1 over x dx, all right? Which, by the way, as a point of notation, guys, we will also write that like this, okay? That's just notation. You know, customary notation used by everybody. Anybody who doesn't use it, they're nobody. So, anyway, what can you differentiate and get 1 over x? What? Natural log of x. That's good. Now I take your natural log of x and I raise you a natural log of absolute value of x. The reason I'm going to do that is because we worked this out. I did. We worked out that the derivative of the natural log of the absolute value of x is 1 over x. So like d dx of absolute value of x is equal to d dx of the square root of x squared, which is 2x over 2 square root of x squared, also known as x over absolute value of x. So if I differentiate natural log of the absolute value of x, I get 1 over absolute value of x times the derivative with respect to x of the absolute value of x by the chain rule. But that is what, I'll get out of the way here for a second, guys, is 1 over absolute value of x times x over absolute value of x, which is x over absolute value of x squared, which is x over x squared, which is 1 over x. Now, you might think this doesn't matter. This is just you and your love of the absolute value is square root of x squared formula. That's true, I do love that formula. I love it too much. I love it more than I should. I'll admit that. It's a problem I have. But this is important because we'd like the most general antiderivative as our indefinite integral. And this formula will work whether 1 over x is positive or whether 1 over x is negative. All right? So like this formula is important to know about because if we're later finding area of like a reciprocal function where we're looking at negative values, if you don't put the absolute value, you're going to get like natural log of a negative number, and then your calculator is going to go, no, you don't, right? And then you're going to know you did something wrong, but the absolute value has to go here generally, right? So, we good? Should we do another? But who's texting me? I tell you, I'm on this group chat. I think I mentioned this for my son's baseball team. It's like every day, like 20 texts. I need to get off that thing. The thing is, I'm always like teaching. I never like really take them to any of this stuff. My wife drives them to all these things. Guess it's good that I know where they are and stuff, but. All right, so next up, you guys tell me how to do this one. The integral of a to the x dx. What is that? What if we just use a to the x as initial guess? Like a lot of times, you just take a step, make a guess, see what happens, right? What is the derivative of a to the x? Remember, it's the natural log of a times a to the x, right? So, what do we need to do? How about this? If we take a to the x and we divide by natural log of a, That should work, right? Because when I differentiate a to the x, I get what? I get natural log of a times a to the x. So that will cancel with the 1 over natural log I put there. And when we differentiate the integral, we'll get back to the integrand. Now, a special case, what's the integral of e to the x dx? Yeah, it's just e to the x, right? What's the integral of e to the minus x? Negative e to the negative x plus a constant. You are correct. That was a guess. But seriously, what is antidifferentiation? It is educated guessing. This never goes away. So at the base of integration is educated guessing. I can straight up derive some antiderivatives from a limit of an infinite sum, but it's so much work that educated guessing is always the better way. All right. Let's see here. Another one. Integral of dx over 1 plus x squared. What would that be? What can I differentiate and get 1 over 1 plus x squared? Nope, doesn't work that way. Nope. I wish, but no. Ay, ay, ay. I tell you, guys. Whew. How about inverse tangent? Remember, the derivative of inverse tangent is 1 over 1 plus x squared. So this is inverse tangent of x plus a constant. What function differentiates to secant squared? Yeah, tangent. So this is tangent of x plus a constant. Which function differentiates to secant tangent? What? Did you say tangent? No. Nope. Yeah, we'll add cosecant squared and integral of cosecant and cotangent down here while we're at it. The answer here is secant of x plus a constant. The derivative of secant is secant tangent. Which function differentiates to cosecant squared? Well, cotangent gives you the minus cosecant squared. So this is actually minus cotangent plus a constant. Likewise, this is minus cosecant of x plus a constant, if I recall correctly. And you can check me on that. The derivative of cosecant is minus cosecant cotangent. This follows from the quotient rule. These are easier up on the top. What's the integral of cosh? Sinh plus a constant, of course. What's the derivative of sinh? Yeah, isn't that so? Sinh and cosh are so nice, you know? What function differentiates to 1 over the square root of 1 minus x squared? What function differentiates to 1 over x squared minus 1? Wait a minute. No, 1 minus x squared, I think it was. 1 over the square root of 1 minus x squared has a domain of minus 1 to 1, because that is the range of sine. This is the derivative of inverse sine. So this is inverse sine of x plus a constant. And let's see here, what else we got? This guy, I'm a little bit unsure, so I'm going to put some scare quotes on this, but I believe this is inverse hyperbolic tangent of x. The quotes are, I'm putting scare quotes because I really should check and be sure. I'm about 90% sure the derivative of inverse hyperbolic tangent is 1 over 1 minus x squared. Yeah, I'm pretty sure that's right, actually, because the domain of inverse hyperbolic tangent is the range of hyperbolic tangent, which is minus 1 to 1. And so that's positive there, which is what I want. Yeah, it's okay. Anything else? Are there any other basic differentiation patterns we know? Like, how about this? What if we tried integral of tangent of x dx? What if we tried the integral of 2x e to the x squared dx? Can you just figure out antiderivatives for anything? The answer is no. Like, there is no basic function that we differentiate and we get tangent is the answer. There's no basic function that we... Wait a minute. Maybe you could guess the second one. What's the derivative of something that gives you 2x e to the x squared? e to the x squared. So we got lucky here, didn't we? And if you want to, this is the natural log of the absolute value of secant of x plus a constant. But so I don't mean to say there's no formula. I'm just saying we don't... These two right here... later. So what I'm trying to tell you guys is, to start with, we learn the basic guesses. We learn those really, really well. And then what we're going to learn is a technique of substitution, which will allow us to convert more complicated problems like these back into the basic problems like those. That's where we're going. That's called U substitution. Anyway, happy Easter to you all. I hope you have a good break. Sorry I went a minute over, but I started 5 minutes late, so I still owe you 4 minutes. Ah.